Suppose I have a spring with spring constant K suspending a mass M. When left alone, the mass hangs at this position, which I've identified as the dotted line going across the page. This would be the equilibrium position. The frame of reference that we care about in this particular example is going to be vertical, which I'm going to define using the x variable. So I'm going to say up is positive x, and that would be from x equals 0 here at the dotted line through the center. So any position up would be positive, any position would be down and negative. Supposing then I take the mass and I grab a hold of it and I pull it some maximized distance down in this direction. If I pull it down this direction and I hold it steady at this position, this would be the maximum displacement vertically down, and so x would be equal to negative a. If I then let go of this system, it oscillates upward due to the power and the force of the spring, reaching this position where x equals 0. However, v is equal to v maximum. The object is now moving here in the center and would be moving upward. As I allow the mass to continue upward due to gravity, once it reaches the highest point, it would stop moving and v would go to 0. And at this point, of course, being symmetrical, x would be equal to positive a. And again, not moving in either one of these positions and moving at the maximum speed here in the middle. If we then go through and define the total energy stored in the system at each position, we could say that the energy here is entirely elastic potential, which has the formula equal to 1/2 kx squared, which in this case is a, and the fact that a is negative does not matter because it is squared. So the total energy can be described as 1/2 k times the amplitude squared. At this position, we know that it is at a 0 equilibrium, which means that the spring is neither compressed nor stretched, which means the elastic energy is now gone because now it is moving, and so the entire energy is now kinetic energy, which can be described as 1/2 mv squared, but of course in this particular case this is the maximum energy, and so we want to be sure to note that, v max squared. So the entire energy can be described as 1/2 mv max squared. Here at the highest point, the velocity goes to 0, so it is no longer kinetic energy, but it is instead back to potential energy, Pe elastic, which again is 1/2 kx squared. X being at the maximum value would be a. The fact that it's positive or negative would be irrelevant, so a squared, absolute value, E equals 1/2 ka squared. And so what we see is at the extrema points, the 3 points that are the maximum energy points, the maximum velocity energy determines the maximum kinetic energy, and the maximum displacement amplitude determines the maximum energy. The ends are symmetrical, which is why we know that this system would oscillate up, back down to the middle, back down to the farthest point bottom, back to the middle, back to the highest point, and so on, considering that energy cannot be created or destroyed. E equals E prime. No matter where we set these things equal to each other, we can describe the middle as being related to either end as being a balance between kinetic energy and potential energy due to elasticity. In other words, 1/2 mv max squared is equal to 1/2 a squared, ka squared. The halves are common to both of these terms, so we have an equation that allows us to put the physical constants on one side and the measurable constants on the other. In other words, to say that V max squared divided by amplitude squared equals K over M. This works for the extreme points. However, there are other positions in which the mass could be moving, as well as the stretch of the spring or the compression of the spring also occurring. These would be halfway or midway or any position other than the extremes. In this case, the mass would be moving this way while the spring is still stretched out, and in this case, the mass would be moving this way while the string is still compressed. It's also possible that these could be moving in the opposite direction in the inverse cycle. Nevertheless, the mass would be moving while the spring is also stretched out. The mass would be moving while the spring is also compressed. So at any other point, these two blue positions, we could say that the total energy is equal to kinetic energy plus elastic energy. But in this case, the kinetic energy is not maximized at the velocity maximum, and the potential energy is not maximized at the amplitude, which means that the total energy can only be described as 1/2 mv squared plus 1/2 kx squared. Before moving on to analyzing springs with circles, it will be useful for us to first combine the midway analysis energy to one of the extremes. The extreme that we're going to use is going to be the end point, where the velocity is 0 and the position is maximized at A. Now, it doesn't matter if it's negative A or positive A, because we're going to square the value in both positions, and so it will be irrelevant. But what we're going to say is that the energy at the end is equal to the total energy at some midpoint or some other position other than exactly in the center. So somewhere unusual. In other words, this subset here. The energy at the end point, where the position is maximized at the amplitude compared to the energy at a midway point, allows us to set 1/2 Ka squared equal to 1/2 mv squared plus 1/2 kx squared. Canceling the 1/2s and rearranging, we're able to generate an equation that ends up looking like this. V squared equal to k divided by m times a squared times the quantity 1 minus x squared over a squared. This is simply an algebraic rearrangement of this equation solving for v. But what that does allow us to do is, if we go back to where we compared the two extreme points, we know that v squared over a squared is k over m, which means that this states that v maximum squared is equal to a squared times k over m. And k over m times a squared is this leading term in this equation we've just calculated. In other words, we can say that the velocity squared is equal to the velocity maximum squared times this quantity 1 minus x squared over a squared. This is useful because this means that we can put the motion of the harmonic oscillator, v, in terms of the maximum velocity, Emax, that the system exerts at any point. So we can say plus or minus Vmax times the square root of 1 minus x squared over a squared. This formula describes the motion of the oscillating mass in terms of its quantitative velocity with a positive or a negative sign based on its maximum speed at the end, at the equilibrium position, based on where it is in the oscillation. In other words, this formula describes the motion in terms of position and maximum speed. And what you'll see, what you notice, is that the mass and the spring constant cancel out. They're no longer necessary in order to describe. So as long as we know the maximum speed and where it is, we can describe how fast it would be moving at any position along the pathway. This, of course, would only be useful if you knew the maximum velocity, but of course you could have calculated it utilizing the extreme points that we had from before. I show you that so that we can then compare this system to an oscillatory system that is very similar yet very different. Instead of a mass oscillating up and down on a spring, now we have a mass directed along a circular path at a tangential velocity v. We're going to assume the mass is consistently held at a distance r, radius from the center of the circle, and is moving at a uniform velocity v that does not change as the mass rotates around the circle. So this would be a uniform, constant, tangential velocity v. In order to analyze the circular motion as a simple harmonic oscillator, we first must isolate one direction. The direction in question for this demonstration will be the x direction. So I've indicated the x-axis here using the dotted line, and we're going to define the center of the circle as x equals 0. And we'll say going this way from the center is positive x, and of course going this way is negative x. Then, just as a brief overview of the mass, if we trace the mass as it rotates around the circle, at the highest position here, directly above the center of the circle, we would say that x equals 0. However, the mass would be moving horizontally at v, which is tangential to the circle the entire time, and so the velocity would be equal to the maximum velocity in the x direction. Conversely, if we trace the mass as it rotates all the way around, and once it resumes its position here, we would say that its position is now horizontally x maximized at what we will call a, the amplitude. Now, of course, we know this amplitude is also the radius of the circle. This also tells us that at this position, the velocity, which would be directed straight up, which would be perpendicular to the x direction and therefore not moving in the x direction, v would be equal to 0 in terms of our strictly held single one dimension. Looking at this as an oscillatory system, then of course we know that over here the mass would simply be moving down, which would be also equal to 0 in our given frame of reference. And then here at the bottom, we know that it would be moving right, which in this case would be a maximized velocity also. Now, this maximum velocity is different than this maximum velocity because, of course, this one is to the right and this one is to the left. So to clarify, this would be the negative direction maximum velocity, and this would be the positive maximum velocity. Nevertheless, the magnitudes of the maximum are consistent. This system, analyzed in a linear or a singular dimension, x dimension, is an oscillatory system. It goes from an initial velocity of 0 at a maximized position. It speeds up as it gets closer and closer to the origin, and it reaches its maximum velocity. That maximum velocity then decreases as it goes back to a maximized position here, where this distance, x, would be equal to negative a. And then as it rotates around to the bottom, it goes back to x equals 0, but now it's moving in the opposite direction at the maximum velocity, goes back to 0 at the maximum position, and continues that over and over and over again. And these things should sound familiar to you because this is exactly what just happened up here. The mass went from a maximum position A to a minimum position of 0 at a maximum speed, and while it was moving up, and then repeating on the pattern back down, it could possibly be moving down, right? And so the simple harmonic oscillatory terms are the same, despite the fact that in this picture, the frame of reference is vertical, and in this picture, the frame of reference is horizontal. Nevertheless, this allows us to do two very important triangles that resolve the system to match the frame of reference. So if we look at our mass at any position other than the extremes, just like we did above, then we can identify this triangle here in terms of position. This triangle, when I measure the distance from here out to any random spot, would simply just be identified as x. And then this position, using the triangle where these are perpendicular, this hypotenuse is, of course, r, but is also a, the amplitude. And so x as a side and a as a hypotenuse yields this side as being the square root of a squared minus x squared. Similarly, with the velocity triangle, we can resolve the velocity that is always tangential to the path as being horizontally to the left in this given position, where this would be Vx, which we're actually just calling V in all of these other terms. And then, of course, this V is the hypotenuse, which we know from the analysis is consistently the maximum value when it is pointed in the x direction, and of course is not considered anything at all when it's pointed vertically. However, what we see is that since this is offset from the x-axis by some angle theta, through some simple geometry and similar triangles, we can see that the angle theta reappears up here in the top of this triangle where Vx is perpendicular to the vertical in the velocity triangle. This is extremely useful because we have two triangles, both containing theta, that can then be put in terms of the given frame of reference direction. In other words, that's to say the sine of theta for the given top triangle would be the opposite, which would be v in this case, velocity in the x direction, just divided by v maximum. Similarly, the triangle at the bottom contains theta, and so sine of theta can be utilized to describe the opposite over the hypotenuse here as the square root of a squared minus x squared divided by the amplitude a. Since the sine of theta is equal to the sine of theta, we can say that v over v max equals the square root of a squared minus x squared over the amplitude. This allows us to solve for v in terms of v max as v equal to v max times the square root of 1 minus x squared over a squared. This formula should look familiar to you as it's what we just derived a moment ago with our spring. And so the velocity equal to plus or minus the v max times the square root of 1 over 1 minus x squared over a squared was derived from an entirely different system, but the system was undergoing a similar motion. It was repeating its pattern indefinitely over a fixed amplitude with conservation of energy. And so the fact that this formula is the same from springs above to circles below means that any overlap of information from one system to the other can probably be ported from one system to the other, right? So this is a proof that whatever we see in springs can be related to circles, which means that if we can derive something new from the circles, we can apply it to the springs with confidence that it is an effective analysis. To do this, we will analyze the characteristics of a circle, which we've previously done and should sound fairly familiar to you. We can say that the velocity around the circle, which we know is the maximum velocity around the circle would be equal to the circumference of the circle divided by the period for the object to make the complete path around the circle. Now, of course, the circumference of the circle can be calculated as 2 pi times the radius, and the radius in this particular example is the amplitude. And so 2 pi a over t is v max. Now, if we solve this for t, we will see that the period of the analysis can be described as 2 pi times the amplitude divided by the maximum velocity. Now, this doesn't seem all that interesting, but if we go back to our spring analysis, we see that we came up with a formula that said v max squared over a squared equals k over m. And that put v max in terms of the amplitude and the spring constant and m. But that relationship is listed right here. V over a over a max is just the opposite of this. So from before, we know that a squared over v max squared is equal to m over k, which means that the square root of m over k is equal to a over v max. Now we've done that so that we can introduce this a over v max as the square root of m over k. This shows us that the period is equal to 2 pi times the square root of m over k. Now, why is that useful? Well, remember, this is describing the period based on a circle, right? We did this through the analysis of going around the circle, the circumference divided by the period, right? We introduced this physical term using the mass and the spring constant, and we were able to describe the period of a circle, a mass spinning in a circle, as being a function of the circle itself, the mass, and a spring constant. Now, there is no spring constant in the circle, right? So there must be something creating a restoring force in the circle. That, of course, is gravity. Gravity is pointed down. F of g is pointed down, which is perpendicular to the direction of x. But perpendicular to the direction of x would create a torque, and so it's reasonable to think that the force of gravity, which is a consistent value on mass, has some sort of restoring value that would cause this thing to want to rotate. And so, although there is no spring constant in the circular motion, there is absolutely a spring constant up here in the spring. And what we were unable to do in our previous analysis was describe the time it takes for this to oscillate. The way we do that is to recognize that since this formula works for circles, then it must work for springs. And so we can use this to calculate the period of the oscillatory spring, despite the fact that it came from an analysis in circular motion. And this will be true for a number of things. If we can describe a system as being a simple harmonic oscillator, then these formulas will work even if there is no spring and even if there is no circle. The example, of course, we will look at is waves, waves that oscillate up and down as the energy propagates from left to right, undergo simple harmonic motion in exactly the same way as anything else that's repeating a pattern for an indefinite period of time. Furthermore, since we were able to introduce these constants, we also see that the period does not depend on amplitude, which will be a key element in waves, as the amplitude does not determine the time it takes for the wave to vibrate.